Welcome to Chapter 23. This is the second part of Chapter 23 where we looked at capacitors in circuits and the homework that was with that. There were just a few conceptual questions and a few problems. So conceptual question 26 asked you to rank, and I screwed up with this first, so I definitely have to think about it. Asked you to rank the capacitances of circuits 1, 2, 3, and 4. Well, these are in series, and of course, I started adding them in series, which is correct for resistors, but not capacitors. So 1 over C plus 1 over C plus 1 over C is 1 over the total. So the total capacitance of this circuit number 1 is C over 3. These are the ones you add, 3C. Here, we add those two, so that becomes 2C. 2C is in series with 1C, so what I ended up doing is 1 over 2C plus 2 over 2C, that does not show up very well, is equal to 3 over 2C. So that's equal to 1 over the total capacitance, so the answer is 2C over 3. It's a little bit difficult there. This one, these two are in series, so I take care of those first. So that means this whole component is C over 2. This component is C. They're in parallel, so we just add those up. C plus a half of a C is 3C over 2. So I get 2, which is this one, is greater than capacitance of 4, is greater than 3, is greater than 1. Sorry for my scratch work. I think we went over that in class. So with this one, immediately after the switch is closed, both bulbs are glowing, probably bright because this capacitor is empty, and therefore all the charge will flow to the capacitor. For letter part B, it was asking about the brightness of the top bulb and the bottom bulb. So this is acting as a series circuit. So despite the fact that over time the capacitor will affect the rate of current flow, since these are identical bulbs and they're in a series circuit, they should have identical brightness at any given time. And over that time, the bulb brightness would decrease as the charges build up on the capacitor. This is very similar to an example I did in class. These two we handle first. 1 over 20 plus 1 over 30 equals 1 over 12. So this is 12 microfarads in this branch. This branch is 25 microfarads. We add those together because they're in parallel. We get a total of 37 microfarads. So that is problem 40. Problem 42 is asking you to find the total capacitance of the circuit. Well, I handle these first. That's 3.5 microfarads. These two are in series, so 1 over 3.5 plus 1 over 4 is equal to 1 over 1.87. So the total capacitance is 1.87 microfarads. This is the formula relating capacitance, charge, and voltage in circuits. So rearranging that to find the charge, that I use the total capacitance, the total voltage of the circuit, and I get that after a long time, meaning the capacitors are all fully charged up, this is the total amount of charge that's held. For problem 49, I changed part B of this because I'm not interested about time constants. But essentially we've got here's a circuit. It's been in this position for a long time, so therefore this capacitor should be fully charged and have a voltage across of 9.0 volts. At t equals 0 seconds, this is flipped to part B. So therefore the voltage across this will be 9 volts. And the charge on it I could figure out using this formula again, which I showed you up here. We're going to rearrange that, and we get 1.8 times 10 to the negative 5th coulombs. To find the current at that t equals 0, as soon as this is switched, I'll use that voltage across the capacitor, which is now kind of acting like a battery, divided by the 50 ohm resistor. Actually, yeah, 50 ohm resistor, not 5.0 ohms, and I get 0.18 amps. After a long time, after the switch is moved to part B, all this charge will have dissipated, and therefore the voltage across the capacitor would be 0, and the current would also be 0. So hopefully that's helpful, and hopefully you, pardon me for yawning, are able to figure out capacitors in series, parallel, and combined circuits.